So welcome everybody, and thank you for joining the seminar this week. Our speaker is Brad Gibson, who's the head of physics and maths and the director of the E.A. Milne Center for Astrophysics at the University of Hull. So Brad's work covers a range of galactic and extragalactic topics, and has gained a degree of notoriety by helping to define the Milky Way's galactic habitable zone and determining the expansion rate of the universe, for which the team was awarded the Gruber Prize in Cosmology, and building the world's first liquid mirror telescope observatory. Brad's also heavily involved in outreach with over 400 events in the last 5 years, reaching almost 1 million people around the world. And his commitment to widening participation and diversity and improving the career prospects of physics students led to his Changing Face of Physics campaign being named the best practice in the country by the UK's Equality Challenge Unit. So it is with great pleasure that we have Brad to speak to us today, where he'll tell us about simulations of spiral galaxies, the good, the bad, and the ugly. So Brad, thank you again for agreeing to speak to us. Please take it away when you're ready.
Great, thanks very much, Ed. Good to see you all. And I think as all these talks start off the same way, wish we could do it in real life, but we'll save that to later in the year, 2022. I look forward to coming down and seeing you all again in real life rather than 2D. So what I'm going to do over the next sort of 45 minutes or so is take a wander through simulation space, particularly focusing on how it is that we simulate spiral galaxies like the Milky Way. I have a separate talk which looks at the history of the field, going back sort of back to Newton, in fact, and going through the 1800s and looking through the really early work in the field of quote unquote simulating spiral galaxies, before the invention of computers and things like that. But what I am going to focus on here is not so much the historical development, but looking at what's been done over the last 10 years or so to bring us closer to getting things that look like real spiral galaxies. There's a lot of things which work. There's a lot of things that don't work. And there's some that are still way off the mark, no matter how they may be sold in publications. So I'll try to spend a little bit more time digging into the things that are generally swept under the rug in terms of what doesn't work, because in some sense that's more interesting maybe than just showing, hey, we've got something that looks good. But I will pepper in a few of the good points in there as well. As Ed was saying, I'm at the University of Hull, so just for those who don't know me, just hopefully let me spend just a couple minutes saying a little bit about the university and the group that we have here, largely because we've only been around for about 5 years, so we're one of the newest astro groups in the country. The uni itself, for those who haven't been here, it's you may have the same mental picture I had of Hull before I got here, which was that it was going to be sort of an industrial wasteland. It's actually a very pretty city. It was the city of culture from 2017 to 2020. Very surprisingly picturesque, very pretty. The area, the old town, the marina, some of which you can see here in the pictures, is actually really beautiful. And the campus itself is actually really beautiful, kind of a classic red brick uni without being part of the red brick group. One of the oldest in the country. It's got a strong scientific history. And John Venn from Venn Diagrams was from here. Arthur Milne, the namesake of our center, was born and raised here. The center, like I said, we established it in 2015. We're up to 25 staff and postgraduates now, largely flavored around high performance computing. We have a 6,000 core cluster that we use within the center for our research, and we're in the midst of a tender process to take it to 20,000 cores later this year. If you're sitting there looking at an LCD screen, they were invented here at the University of Hull at a time when the university was not really up on patent law, and so they missed the boat on getting the patent on LCD technology. George Gray himself, who invented it, fared quite well, but unfortunately the university missed out on reaping the financial benefits of that. And something I only learned very recently, the first moon rocks that came back from Apollo 11 back in '69, they were actually brought here. At the time, the applied physics group had sort of the leading equipment, instrumentation for doing this sort of a analysis. So the very first scientific papers that came out on analyzing the moon dust and moon rocks, in particular, they're looking at reflectivity and how the grains settle differently in different gravity on the moon versus here. Those very first papers weren't from, no disrespect, Cambridge and Oxford and Chicago and Caltech, but actually little old University of Hull. So that was something I had no knowledge about until the 50th anniversary came up a couple of years ago. So there's sort of this rich history to the place, just to give you some context. Like Ed said, we're a big focus of what we do is around outreach and engagement. We're still doing, obviously, research and teaching and all the things we're expected to do, but I'm also not naive. The university saw astronomy and astrophysics as a way to sort of engage with the region, one of these powerful STEM enablers, dinosaurs in space. That's what kids like and what the next generation like. We've done about 500 events over the last 5 years or so. I think I've done about 450 of them. If you take about 3 million people that are there, largely that's driven by things like my TED Talk and various other online things. We've done about 250 school and college events across the country, largely focused around the region. But you can sort of see the spread around the country here this is, I think, 450 events around the country that we've done. It's not about recruiting to Hull. It is really about reaching into particularly areas where you're in the bottom, what we call the quintiles, and the various socioeconomic metrics that are used. So it's reaching into regions of the country largely, which sometimes may get forgotten, and providing that, hopefully, that inspiration for that next generation of kids to continue on into the STEM subjects, wherever they may be living. As you can probably guess, I've made this pretty picture because this is part of our REF submission, which I'm working on right now. So if you are an assessor for REF, you may be seeing this figure again in terms of the impact of what it is that we've been doing. Been lucky to work closely with a number of people who have similar ethos in terms of widening participation. These are people who are associated with the center, and you will know most of them. The Astronomer Royal to discover pulsars, Jocelyn, and Helen Sharman, the country's first astronaut, is from not too far from where I'm sitting here in Hull. They're not just there as celebrity names. They do, pre-COVID, would come up a couple times a year, come into schools and colleges with me, talk about their experiences, because again, they have that same mindset of trying to widen participation, particularly into again, these bottom quintiles of socioeconomics and monetary deprivation as government labels. This is not this bunch of my students over here who sort of are the primary liaisons when Helen Sharman comes to visit. This is not one of our students. That is my daughter, Esme, who loves to wander around school talking about how she's friends with Helen Sharman, gives her some street cred. And Michael Foles, also, for those who don't know, the country's most decorated astronaut, one of the few who spent more than a year in space, is also not far from, comes from not too far from where I'm sitting right now in Hull. And the last thing just to say is, Hull is the poorest city in England. I think it's the second poorest in the UK. I think it's only 1 in 10 16-year-olds go on into higher education of any form. And it also has had a huge impact on the demographics of our physics cohort, where up until maybe 6-7 years ago, typically it was 10 to 12% of the first year cohort were women, which is about a factor 2 below the national average. So we've put a lot of effort over the last 5 years into not just widening participation in a socioeconomic sense, but in terms of our gender diversity. And I was lucky to have a bunch of students who had a similar passion for doing this, and they've all been very supportive in the work that we've done as part of this Changing Face of Physics campaign that Ed alluded to, which involves a lot of work with regional schools and colleges. Normally when I go into schools and colleges, some of the students come along with me. They talk about their experiences coming from the same demographic, the same background, socioeconomically speaking, as many of the students that we're engaging with. And they're all amazing sort of peer role models and have made a huge difference. It's also really resonated with our alumni who've been very generous in donations to support this diversity agenda. All of the students have been supported by bursaries. We secured another generous set of donations to support another 5 students who have their funding covered. And they're helping me with the next phase of this changing face of physics campaign. And one of the success stories of this is one of the 4 inaugural Jocelyn Bell Burnell Fellows, Kiri Newson, who did astrophysics with us, is now taking that skills that she's acquired in applying AI machine learning algorithms to astrophysical images into the medical physics community. So she's just started her PhD as a Jocelyn Bell Burnell Fellow. So just to give you a little bit of context as to who we are and what it is we do and where the focus of our efforts are based right now. So anyways, what you guys are probably sitting in to hear about is how well do simulations of galaxies recover what we actually see in nature. And if you're an observer of galaxies, all depends on what your interests lie. It may be things related to the stellar distribution. It could be the chemical abundance gradients in disks. It could be surface brightness profiles, the distribution of metals in a given region, say the solar neighborhood. There's any number of things related to stars that may pique your curiosity for teasing out the physics that shapes galaxies. If you're working at a different wavelength, you may be more interested in sort of the gas distribution. Again, things like velocity dispersion profiles, how the power spectrum of the ISM looks, how superbubbles are distributed, how galactic winds operate and circulate metals and gas from the disk to the halo and back down again. These are all things that observational astronomers use to slice and dice galaxies. And as a simulator, what we try to do is observe our simulations as close as possible to the same way in which observers would do that, and try to tease out whether we've captured the physics correctly and at least consistently, if not correctly, with how it operates in nature. And so what I could sit here and I could focus on any number of these. I'm not going to sit here and walk through every one of them. I'm going to pick and choose a couple of interesting ones that work and a couple of them that don't look so good. There's lots of gory numerical stuff that one could spend time talking about, lots of things hidden away down here in the bottom left pile. And I will pick out a couple of them, but again, I'm not going to go into any of the gory numerical details. So if I wanted to, is this actually going to work? Yeah. If I wanted to boil down, keep it really simple and put it in one slide, what is it that, what is the physics that shapes a simulation? And look, you've got the primary physics, it's A-level physics mostly, it's gravity, and simple laws of fluids, viscosity, and not a whole lot more. Now, obviously the devil's in the details, and I'm not going to go through all the numerical algorithms, how you implement time stepping algorithms. But, the one thing to remember in the back of your mind is that, the physics is not complicated. It is sort of that A-level physics. How you implement it and how you capture it inside of your computer is where the challenge is. And if I were to boil down what it is that goes into, say, a simulation that you may be seeing there on the screen now, what is it that shapes what this gas is actually going to end up looking like? Is it going to look like a blob, an irregular, or a spiral? And the short answer is that the whole thing boils down to feedback. And it's a very broad term. By that, I mean energy feedback. How do I implement the energy associated, say, primarily with supernova, exploding stars? In our own galaxy, we've got a supernova goes off once every 10 years or so. Each one of those is, 10 to the 51 ergs of energy. So you've got over the course of over the lifetime of the disk, you've had a billion supernova have gone off, something like that. And so that's an enormous amount of energy to play with. I mean, the sum total of that energy, 10 to the 51 times, a billion supernovas greater than the binding energy. So you can see there's a lot of energy there to play with. And so as a simulator, you have to make some decision as to what are you going to do with that energy? Every time a star explodes inside of your computer, you've got that 10 to the 51 ergs of energy that you need to make a decision about. And it boils down to, you can see in this in the third bullet point, of sort of efficiency factors. How efficient does that energy couple to the surrounding gas? It could be very efficiently, in which case you might take all of that energy and put it into either heating the gas in a thermal sense in the surrounding region, or you may decide you're going to put it into kinetic energy and give a physical push to the gas particles, if you like, and have them moving away from your explosion site. Or you have some interplay between kinetic energy pushing the gas and thermal energy heating it. You've got other things that you have to think about in terms of feedback of energy. Now, in a late type spiral like the Milky Way, yeah, we've got we've got a supermassive black hole at the center, but it's a fairly conservative one in the grand scheme of things. If it was a much bigger one, we might be a little bit more concerned with capturing the feedback of energy from the AGN, based on the duty cycle of the feeding of the AGN. It becomes more important as you get to more and more massive galaxies and early type systems, but I'm not going to spend any more time on that. If you just took the surrounding interstellar medium of the disk, we have something that's called equipartition of energy, more or less, with roughly a third of the energy tied up in supernova turbulence, if you like, that I've just described, a third of it in cosmic rays, and a third of it in magnetic fields. Most of the simulations that are out there, including most of the ones I'm going to be showing you, ignore 2/3 of those. The vast majority don't take into account magnetic fields, and the vast majority don't take into account cosmic rays. So you've already got a reason to sort of start questioning some of the physics of these beautiful, elegant disk simulations that people show, including the one that I'm showing you right now, largely because we only, for the most part, 95% of the cosmological simulations out there of disk galaxies are only taking into account the effect of supernova and basically hiding the missing physics from cosmic rays and magnetic fields inside of the supernova feedback prescription. And I've ignored, for what I'm showing you right now, not for some of our other work, the effects of AGN. So this is what it is. It's feedback of energy and how efficiently you allow that to couple with your surrounding interstellar medium. Now, so how do we get the physics correct? The simulations that I just shown you there, and the majority of nice looking disk galaxy simulations are working at a spatial resolution, if you like, of couple hundred, 300 parsecs. So you're not down at the level of resolving individual star forming regions. Now, you can do targeted simulations that zoom in on individual star forming regions, work at very different scales. But for these sort of disk scale simulations, that's the typical resolution that you'd be working at, a few hundred parsecs spatial resolution. Obviously, supernova and an energy feedback from stars before they explode, they're obviously working at a much different scale than that. So no matter how clever that you may be in terms of the analytical way in which you think to include that energy into your simulation, we're working at very, very different scales. And so one typically has to put in one of these efficiency factors to hide the subgrid physics that we don't actually resolve. And we have to calibrate that efficiency factor to ensure that you at least recover one relationship. Doesn't necessarily mean that you try to recover all the relationships, and I'll show you that in just a second. But the majority of the famous simulation suites that are out there, so things you will have heard of, perhaps things like sort of the Dutch, German, UK Eagle simulations. You've got the Lustrous and the various variants of Illustrious in the primarily US driven, and our own small little contributions, Magic, making galaxies in a cosmological context. There is one common calibrator that is used to set some of these efficiency factors, and that is the relationship between, in a galaxy, the stellar mass and the halo mass. So observationally, this is what we see. This is a stellar mass on the y-axis, halo mass on the x-axis. So the gray region and the line cutting across diagonally, that is the sort of empirical relationship between stellar mass and halo mass. And if you go back 10 years or so, the simulations that existed 10 years ago, 20 years ago, 30 years ago, they had a tendency to sit above this relationship by typically maybe an order of magnitude. In other words, for any given dark halo mass, we would overproduce stars by, say, a factor of 10 or so. And that was independent of any particular group. There's, again, an enormous literature about overcooling and all kinds of other things we're not going to go into, but that was the standard problem, using the best guesses as to what the analytical prescription should be for how energy feeds back. You overproduced starlight. So the approach that we took when we started, and others, as I'll show you in just a second, have done, is to calibrate at least one of those efficiency factors to place your galaxy onto this relationship between stellar mass and halo mass. And so that's what we did. We took one of our simulations, and that is what this yellow diamond is, and the star formation efficiency that we put in, I'm going by memory now, but something on the order of between 1% and 2% of the gas. Anytime the gas got to a critical threshold where the density would suggest you have some sort of statistical likelihood of stars forming, we would allow between 1% and 2% of that high density gas to turn into a star. And that is what, for that one simulation that we had generated, placed that galaxy on the stellar mass halo mass relationship. We didn't look at any other scaling relation at that point in time. We didn't try to calibrate that efficiency factor to anything else. It was just one single efficiency factor, which was that normalized star formation efficiency, and that placed that simulation onto that empirical relationship. Now, having done that for that one galaxy and being confident at least in that one relationship, which is kind of repeated up here in the top left, the stellar mass, total mass relationship, if you like here, that galaxy, which I think is that yellow diamond, hopefully where you can see my cursor. We then ran a bunch more simulations, not a whole lot, but there's 6 or 8 simulations that we ran with some dynamic range in sort of stellar mass of maybe 3 orders of magnitude in stellar mass, and 1.5 orders of magnitude in total dynamical mass. So having one galaxy calibrated to sit on this relationship, all the other ones also fell on the relationship. It's not a huge dynamic range, I know, but at least those 6 to 8 simulations that we ran with that same calibrating efficiency all sat, at least over some dynamic range, sat on the empirical relationship between stellar mass and halo mass. If we had used the classical approach of doing this, which existed up until 2012, which is more or less, if you want to keep it simple, maybe only 10% of the energy from the supernova would go into coupling strongly with the surrounding interstellar medium, and the other 90% would just radiate away without really having any impact on the surrounding ISM. That's where one of these simulations would have sat. It would have sat up in the same region that all the other simulations sat in up until that point in time. So having done that with one, the other 6 or whatever all sat on the scaling relation, then we did the next step, which is what at that point in time others were not doing, which is then go and look at every single other scaling relation that we could think of off the top of our head. And so we came up, there were these 8 scaling relations for galaxies, and black and gray and all of these is observational data, and the various green and yellow are using the single calibration for star formation efficiency that we used. And what you can see is that, moving from the stellar mass halo mass relation, the next panel over is your Tully-Fisher relationship. So circular velocity against luminosity. All the yellow and green sit right amongst the data. I'll come back to the red triangle in just a second. Size, line width relationship looks good. Size, luminosity. There's the mass metallicity relation in the bottom right over here. Gas to light ratio, if you like, baryonic Tully-Fisher relation, specific star formation relation. So having calibrated one galaxy to sit on that stellar mass halo mass relationship, all of the simulations that we ran at that time, at least over that dynamic range, all of them sat in amongst the observational data. It was the first time that we've been able to actually do something like that. And so you can see one of the issues that existed, if you go back and look at papers from the 1990s, 2000s, up until this point in time, what others had a tendency to do is, for example, see that when I look at the Tully-Fisher relationship, this galaxy, which overproduced the number of stars, and which is why it doesn't sit on the stellar mass halo mass relation. If all I did was write a paper saying we've got a galaxy that beautifully is consistent beautifully with the Tully-Fisher relation, as this red triangle is, you could deep dive into that, analyze it like crazy, do all kinds of work, talking about a disk galaxy that was consistent with the Tully-Fisher relationship, which is true, but that same galaxy is clearly not consistent with, it's got the wrong mass of stars, it's got the wrong size for its line width, it's clearly used up too much gas compared to overproducing the stars. So you have to be a little bit careful in interpreting some of the works that existed through the 90s, 2000s, and perhaps even today. When somebody shows a result for a simulation that agrees with one scaling relation, it's worth asking the question, how does it compare with all the other scaling relations? Is it consistent with them? But at least at that point in time, we had a suite that was consistent, which was nice. So you can look at, and that's how we did it in MAGIC, and that was the point I'm making right here. We calibrated everything on one relationship between stellar mass and halo mass. Now, the much more famous, bigger groups like Illustris and Eagle, they also use a stellar mass halo mass relation. It is one of the fundamental calibrators that they used in generating these gigantic mega suites, Illustris and Eagle. But their approach was they had a much larger multi-parametric calibration process than we did, which was one galaxy calibrated to one scaling relation. They used the stellar mass halo mass relation, for example, Illustris, just like we did, but they also at the same time made sure that as they were doing these cosmological simulations, that they were also recovering the cosmic star formation rate, the relationship between star formation rate and redshift. And Eagle took an even bigger approach with a much larger multi-parametric survey of parameter space to ensure that their simulations were calibrated to recover not only stellar mass halo mass, but the stellar mass function, the size luminosity relationship, and the black hole mass stellar mass relationship. So this is something to bear in mind when you, and I'll show you in just a second, when you are comparing, say, the works of MAGIC, what we did, versus Illustris, versus Eagle, versus the image that you're seeing here, Magneticum, there's Horizon AGN, there's a whole bunch of groups out there doing various things. Each of them calibrate on different things. And so somebody may present a result that looks exquisitely similar to what you see in nature, but you do have to ask the question always, is that because your simulation was calibrated to recover that, or was it a prediction of the simulation? So just as an example of that, and this is not passing judgment on anyone, it's just being careful about the terminology and how it's presented. So for example, on the left here is the stellar mass function, observationally in the various colored open symbols. And then the lines in red and black are the Illustris simulations at the time. And so what you can see is that, that over some dynamic range, the predicted stellar mass function does agree with what you observe in nature. But when you move to the high mass end and the low mass end, they don't agree. And it shouldn't be, necessarily shocking because the stellar mass function, as you can see on the list on the right here for Illustris, was not one of the things that they used to calibrate. Now, if Eagle were to show you the same plot, you would expect it to agree better than Illustris because the stellar mass function was one of the calibrating scaling relations, if you like, in generating Eagle. Conversely, you would expect the cosmic star formation rate to be recovered in Illustris, which it is because it was a calibrator, whereas in Eagle, it was not. And so what you can see when you look at, for example, on the bottom right is the cosmic star formation rate from one of the reference runs from Eagle. And what you see, the solid curve, the shape is right, which is great, but it underproduced star formation by a factor of 2 or so. And that's why they apply a 0.2 dex increase to bring it up into agreement with the observations. It's not it's not some damning indictment in any way, shape, or form of Eagle. It just shouldn't be shocking that it doesn't recover perfectly because it's not one of the calibrating points. you could also look at, for example, the gas fraction. So sort of a messy plot, but it's more or less the ratio of gas within 500 kiloparsecs versus the total mass versus the mass of the halo. So you can think of this as gas mass in clusters, for example. And the various cluster gas fractions are over here in the gray symbols. And then you take the reference run for, this would be for Eagle. And it's not surprising that it's, the reference run sits again a factor of two too high, because it wasn't one of the, getting the gas fraction right wasn't a part of the gigantic multi-parametric survey that they had done. So again, their predicted value, while they're consistent with all of their calibrators, the predicted ratio gas fractions don't necessarily match up. So again, it's, if you take nothing else from the talk, it's not being skeptical of anything that you see presented. It's just always good to ask that question: was that simulation calibrated to recover that, or is that an actual prediction? Okay, so I'm just going to go through a few things that, in green that look good, a few cautionary things in yellow that I'll touch on very quickly, and then there'll be some color-coded things in red which don't work so well. Okay, so what is one of the good things that works as I go through good, bad, and ugly? If I look in the solar neighborhood and just take stars around the sun and look at the ratio of an element like magnesium to iron, it's hard to read across here, plotted against iron. Well, you see, it's not a random distribution of points. There are two sequences that stick out in the top right here. There's one at any given metallicity with an elevated magnesium to iron, factor of 2 or 3. And those are stars that we now associate with the thick disk. And then there's a sequence underneath it, a couple tenths of a dex below, which are stars that, for a given metallicity, have lower magnesium to iron, closer to the solar ratio, which is 0 on the scale. And those are the stars that we associate with the thin disk. And there's, like I said, the separation of 0.1, anywhere from 0.1 to 0.2 dex between those two sequences. Now, even back in my PhD, we sort of had the data wasn't anywhere as nice as that, but we had an understanding of at least what could potentially drive those two sequences. And basically it comes down to having an intensive burst of star formation or star forming epoch in the early galaxy, with the rapid turning of gas into stars, type 2 supernova, which drive a high magnesium to iron being the primary pollutants. And then something quenches or stops the star formation for a while. There's a cessation of star formation. Gas continues to fall in, and then a new cycle starts, which would be the thin disk, which starts having been diluted. It comes down to lower magnesium to iron and shifts over to the left to lower Fe on H. And so you get these two sequences that are offset from each other. And depending on any given galaxy, might have a more extended cessation of star formation. And what you could have is the two sequences could be offset and start from the same place, or they could be offset and start shifted one direction or shifted the other direction. But the two sequences come down to a cessation, a hiatus in the star formation. So like I said, we've known about that, 20 years or more, 25 years or more, that was likely, or at least that was one logical explanation as to what could drive these sorts of offsets between the thick and the thin disk. And so what we did with one of the first simulations that I showed you was do that. We just went into the solar neighborhood and plotted those ratios against metallicity. And there's no tweaking or fine tuning. It's just taking one of those simulations. And what you can see is there is, I'm not going to try and make too much out of it. There's a sequence up with a higher alpha to iron ratio, and a sequence down below, which has a lower alpha to iron ratio. It doesn't match 1-to-1. It's not meant to be a 1-to-1 match to the Milky Way, but there is a kind of a 0.05 dex offset between what we would call the thick and the thin disk in that simulation. And we can go back to the simulation and look at the star formation history, and we can see there's this sort of intense burst or period of star formation. And then there's a dip. It doesn't go all the way down to 0, but it does drop by a factor of a few. And that decrease, that hiatus, that cessation, whatever you want to call it in star formation, is what drives this transition from that elevated alpha to iron to what you see below. So that, again, not a one-to-one match. Now we now have many more simulations to draw upon. We can play the game of wandering around trying to find closer analogs, if you like, to the Milky Way, ones that have a deeper dip in the star formation. And so I can pull one out like this, which does a bit better job, if you like, of getting a cleaner separation between the thick and the thin disk. But the physics that's driving it is exactly the same. So we didn't set out to show this, but it was a nice consistency check on sort of the analytical predictions that Francesca Mattiucci and others had made using analytical models of chemical evolution. It came about naturally inside of these simulations that had been calibrated to at least recover the stellar mass halo mass relation. So that is a good recovery of sort of the broad abundance patterns. We can look at other things like the ratio, not as a function of metallicity, magnesium to iron, but we can look at magnesium to iron, sort of cut off the axis labels, against age. And we've known for the last 5 years or so that this ratio of magnesium to iron as a function of age for stars in the solar neighborhood, it's a good clock. I mean, there is some degree of scatter in there, but it's actually a remarkably tight relationship between the ratio of magnesium to iron and age. So it is something of a cosmic clock, cosmic chronometer using magnesium to iron. And so this is, when we take one of our simulations, that's one of my PhD students, Leah Cox, is working on this right now. Take one of our simulations, which all the black points there, the symbols that you can't really see very well, there's just binned up versions of the data there. And then we've got some analytical models overlaid on top. But we haven't done any playing around with the simulation to try to set the trend of magnesium to iron versus age. These being calibrated on something completely unrelated has actually very naturally led to this cosmic clock that is consistent with what you observe in nature. So that relationship between chemistry and age has actually been recovered without any fine tuning. So that's again a nice thing. Some things don't work so well, and there's some things that would be very difficult to recover. Again, very busy looking plot, but what this sort of screen grab on the left is the ratio of two other elements. This is sodium to magnesium, and there's no simulations in here. There's no chemical evolution or anything. It's just taking the predictions of nucleosynthesis from different stellar nucleosynthesis experts. So the predicted sodium to magnesium is a function of the mass of the star, which is along the x-axis. And if you look at, say, a galaxy like M87, a giant elliptical, what you find is that if you look at the integrated light, that the ratio of sodium to magnesium, it's not the solar value, which would be around 0. It's elevated, again, by a sort of factor of 2. It's twice as much sodium relative to magnesium compared to what you see in the sun, for example, which is what this yellow band across here is. So if I were to run a model with simulation or an analytical chemical evolution model using these yields, which are listed here and plotted up in this messy way, I've just drawn across here. You could probably look at that and say, look, I can imagine I could take a distribution of stars that would give me an elevated sodium to magnesium, regardless of the star formation history. There are some stars that have higher values and there's some stars that have lower values. So you can imagine taking a distribution, what we call an initial mass function, and it shouldn't be shocking to imagine you could come up at least with some sort of model that would give you an elevated sodium to magnesium. Problem is these, if I take the best yields that are around today, Marco Pignatari and his team, the New Grid folks, the absolute best yields that exist on the market today, all kind of sit low. It's very difficult to look at the best yields on the market today and figure out how could I convolve those stellar yields to give me an elevated sodium to magnesium. There's only one model that really sits up there very high. So you'd have to have a really strange initial mass function that really only sees the impact of, in this case, 25 solar mass stars. It's very difficult to convolve across a reasonable distribution and get anything that varies dramatically from sort of the solar value. So if you're interested in recovering things like the solar neighborhood and bog standard galaxies like the Milky Way, these yields look like they'll do the trick, not a problem. If I wanted to run a model for giant ellipticals, there is something inside of those yields which is not going to work. There's nothing I can do with any model a realistic model that's going to give me the abundance pattern that I see in giant ellipticals, for example. So you have to be aware that there's some underpinning issues with the stellar yield. And if you really want to drive that home, everything I've talked about thus far and almost everything that's done in the field of chemical evolution, including how it gets fed into all the different simulations that I've shown you, they use one-dimensional models of stars. They do not use two-dimensional or three-dimensional. They're a lot more computationally intensive. So you do all the stellar evolution in 1D, and then you blast a shock wave through it and get out your predicted yields for all your different chemical elements that you might be interested in. And this is a kind of just a cautionary statement more than anything else. This is one model for a 23 solar mass star, typical high mass star that's going to explode as a type 2 supernova. If I run it, standard in this table means the typical one-dimensional model where you get a certain amount of iron. This is radioactive nickel, and you get various predicted values of what the oxygen to iron and silicon to iron, blah, blah, blah. Now, if I were to run the same model and for the same neutrino luminosity for this exploding star, then that's what the second line is. And this is using a three-dimensional model. So a 3D model gives me a much larger remnant. Basically, I don't get any iron out whatsoever, which gives me all kinds of crazy ratios later on. If I were to take the same model in 3D, but force it to get more or less the same remnant mass, 1.6 solar masses, I need to crank up the explosion energy a little bit. Okay, that's not crazy. But then when I do that, you know, I double the amount of iron, the oxygen goes up a factor 3, carbon goes down a factor 3. So the reason I put this in as a cautionary statement is there's an enormous literature of chemical evolution models out there, including all the stuff that I've done for my PhD and subsequent, that is all underpinned by the stellar nucleosynthesis, largely done in one dimension. But this cautionary statement shows you the values can change quite dramatically when you move from 1D to 3D. So this is an ongoing thing, and we're making huge strides with the New Grid collaboration. People, like I said, Marco Pignatari and Raphael Hershey-Kiel and people like that are we're trying to bring these huge discrepancies that exist between 1D and 3D, and they are getting closer and closer together, but one has to be a bit cautious about delving into gory details of simulations that are underpinned by one-dimensional nucleosynthesis. And the only numerical thing I really want to talk about sort of in the last 15 minutes, there's two things I really want to cover, and that's metal diffusion. Again, there's lots of gory numerical details that go into all these simulations, whether it's Eagle, Illustris, Magic, the ones that I've shown you thus far. The particle-based approach to doing hydrodynamics, which is what underpins, for example, Eagle and Magic anyways. They're predicated upon smooth particle hydrodynamics. So that means your fluid is split up into particles. And the problem, but it's one of the challenges that's associated with this approach is that unless you tell these particles as they pass each other in the night, you can have a hot metal poor gas particle going past a cold metal rich gas particle. And a particle is a particle. If you don't allow those particles to diffuse information as they spend time together, they'll just sort of go past each other. And that particle remains hot and metal poor, and this particle remains cold and metal rich, for example. Obviously, in nature, when you mix a cold gas and a hot gas, they become a warm gas, and their metals share as well. Now, this gets captured a lot more naturally, let's say, in the grid-based approach to hydrodynamics. But in the particle-based approach, you have to put in this treatment of diffusion to allow that information to share. And this just shows you one example of that. If I run a simulation, our traditional simulation that we've been using in Magic, which has a fairly efficient treatment of diffusion, the relationship between metallicity and this is age along the x-axis cut off again, you get this tight chord, old things are metal poor, young things are metal rich, relatively speaking, with not a whole lot of scatter at a given age. And I can crush that down and make a distribution function, a metallicity distribution function, and obviously it's quite narrow. If I were to turn off diffusion altogether and just let the particles stay with whatever metallicity I have and never share that information with neighboring gas particles, I get something which has kind of broadly the same trend. Old things are metal poor and young things are more metal rich. But you can see without doing any numerical analysis that the scatter at any given age is much, much greater. So how you put in the gory details of diffusion, metal diffusion, numerical diffusion in there, makes a huge difference on the scatter. So if you are interested in things like the relationship between age and metallicity, or the metallicity distribution function, which are things that both are things that I'm interested in as both an observer and a simulator, you have to be a little bit cautious about exactly how you treated diffusion inside the simulation when you're querying people, or where you see simulators making predictions. It's, you know, within your right to ask the question whether they've actually captured the diffusion correctly or not. Another thing that seems to work pretty well, or at least it's interesting, is the evolution of the metallicity gradients in these simulations. So this is a measure of the steepness of a metallicity gradient, flat up here, very steep down here, as a function of look back time from the right, so in redshift. Observationally, it's what you're seeing in these various open symbols. As you go to high redshift, there are a number of galaxies that appear to have very steep metallicity gradients. Now, if I take our simulations with actually weak feedback, conservative feedback, that's what these green curves are, they actually agree with what you see with those very steep gradients at high redshift. You can think of that as if feedback is weak, when stars explode, the metals that they return sort of stay where they are, because star formation occurs more in the center of the galaxy. The metallicity builds up in the center more, so you get a steep gradient at high redshift before it flattens out. With strong feedback, which is sort of up here, you would expect when stars start to explode, they blast metals all over the place, and so you have a fairly flat gradient, and it doesn't change a whole lot with redshift. And so our simulations with strong feedback, the magic simulations that I talked about, are these green and black, the blue and black curves are going across the top there. So both, whether you have strong feedback or weak feedback, there's a degeneracy today. They both agree with the gradients that you would predict today. But once you get past a few tenths in redshift, 0.5 or so, then they do start to diverge. And actually the predicted metallicity gradients at high redshift become probably the strongest discriminator between this particular ingredient of subgrid physics. There's a lot of things that are degenerate between strong feedback and weak feedback, but this is one of the ones which clearly separates. And so that difference in gradients at high redshift can be a very powerful diagnostic of how strong or efficient the feedback is. Maybe what I'll do is move on from the CGM, the circumgalactic medium, because I want to end on a couple of other points. In particular, this is sort of the last science point I want to make in terms of hidden gremlins, if you like. And it's how you actually observe your simulation. And to me, maybe this is the most important scientific thing maybe to take from this talk. Now, if I were to ask someone to take 100,000 stars from a cluster in nature and plot it up in a color magnitude diagram, you'd see the sorts of things that you recognize from Astro 101 first year. Typical, you've got your main sequence and giant branch and turn off and horizontal branch and white dwarf sequence, etc. So that's what a few 100,000 stars from a cluster in nature looks like. And now, what does that look like to me as a simulator, or someone from Durham, or someone from MIT doing this with Illustrious and Eagle? What does a few 100,000 stars look like to them? Well, it looks more like something like this. It's a single point. So you can see you've compressed an enormous amount of information into a single star particle. And we call them, they're really composite particles, because they're typically maybe tens of thousands, 100,000, somewhere between 10 and 100,000, depends on the resolution. But you're looking at a few tens of thousands of solar masses inside of each star particle inside of a simulation. But those are the particles that we actually examine. So whenever I've shown you anything, color magnitude diagrams, or if I've shown you an age metallicity relationship, what I'm doing is I'm stacking up a bunch of these things and asking the question, is stacking up a bunch of those the same thing as taking, say, a color magnitude diagram in nature, say from 2 mass like this, and selecting out a subset of stars. This is how, for example, the Gaia ESO survey, that little blue box that you see there, those are the stars that the Gaia ESO survey selected for their analysis of doing galactic archaeology in the Milky Way. When I'm a simulator, typically I wouldn't have that information. I just got these composite star particles and I use them as a proxy to compare against these. So it's worth asking the question, are we analyzing those simulations correctly, or at least in a way that's self-similar to the way in which observers will be doing it? And that basically, how I've just described it is underpins 99% of the work that's been done in comparing simulations with observations, whether it's, these top panels are metallicity distribution functions for a particular region, just the distribution of stellar metallicities, or 0 is solar, -1 is 1/10, or the relationship between age and metallicity, or the relationship between ratio of chemical elements and metallicity. All of those, doesn't matter if it's, my paper or any of these other papers, that's what they're doing. They're taking out these composite particles from the simulation and making a plot like this, and then comparing it with observational data, which is obviously made from actual real stars that have been selected with some reasonable selection function based on color and apparent magnitude, for example. So I just want to show you, going to show you one example of this, where this could be important. How you examine the simulation can be as important as the physics. So this is a big, busy table. I don't want you to take a whole lot about it, but there are different ways that you can measure. In the top panel, you see the metallicity distribution function. If it was a nice Gaussian, you might measure the sigma in the distribution. What you can do is you can measure how skewed it is. There's different, different moments of the distribution, the skewness, kurtosis, how much it differs from a pure Gaussian. Absolute numbers don't matter at all. You just look at the numbers, you can see them vary. It's the same simulation run with different physics, different initial mass functions, different radiation pressure, different cooling shutoff points, different treatments of diffusion. So the main point is you can see the skewness changes and the kurtosis, the shape of the distribution changes depending on the subgrid physics that I use. And that's been the focus of almost 20, 30 years of doing simulations. It's all been about capturing the subgrid physics correctly. And you can see by varying that subgrid physics, that's the impact it has on this one particular metric in metallicity distribution functions, skewness and kurtosis. So what I can do inside of my simulation is for each of these composite star particles, I know the age of the star particle, I know the metallicity of it, I know the initial mass function that I ran the simulation with. So what I can do is I can take that composite particle and blow it up and plunk it down onto some isochrones like this, and I can populate the isochrone with the correct number of real stars in the right place, which allows me to get, for the 10,000 solar mass composite particle, I can actually get the correct number of 0.5, 0.6, 0.8, 1, 2 solar mass stars. I know the colors of those stars. I know the luminosities of those stars. And so we do this using this tool that we call synthetic CMD tool that built on the back of things that Daisuke Kawata and his team were working on. And so we did that. We put ourselves inside the simulation at the solar neighborhood, and we selected stars exactly the same way that observers would do. And I'll just show you the one example, which is using the radial velocity experiment, RAVE, that I was part of. So in RAVE, it's a very simple selection function. We sit ourselves in the solar neighborhood, we avoid the galactic plane when we select stars, and we basically took everything that had an I-band magnitude between 9 and 12. It was using UK Schmidt telescope at the time, what it was called in Australia, and ran that for almost a decade, collecting radial velocities and metallicity information. And so we can do exactly that. We can put ourselves in the simulation, we blow up all the composite particles into individual stars using the isochrones, and then we pull out, in this case, all the stars between, this is the apparent magnitude CMD, where I just select stars between 9 and 12 inside of the simulation, exactly the same way that we did with RAVE. If I want to get clever, I can also select dwarfs versus giants, because we also did things like that within RAVE with the observational data. So I'm just going to show you this conclusion, and again, just as a cautionary tale more than anything else. So again, busy plot, but in this thick black curve, which is the metallicity distribution function, that's the measure of the skewness and the kurtosis I would get if I use those composite particles that the simulation spits back to me. if I were to take those particles, blow them up correctly into individual stars, and then just pull out the stars between 9 and 12, the way we did in RAVE, then I get the thin dark curve there. So you can see how the skewness changes and the kurtosis changes. If I want to play the same game in separating giant branch stars from main sequence and subgiant branch stars, again, you can see how the skewness and the kurtosis changes depending on how I select my stars. And so again, the absolute numbers there don't really matter. The main thing that I want you to take from that is that the values are changing at a level that's comparable to the values, how they change when I change my initial mass function, when I change my subgrid physics of energy efficiency, or I change my subgrid physics associated with diffusion. Something that's been more or less ignored in the analysis of all of the simulations that have been done to date is that how you look at the simulation can have just as big of an effect as the subgrid physics that underpin the simulation that you ran, which is where, again, 99% of the effort has been spent in the last couple of decades, has been on that subgrid physics rather than how you actually observe it. So that's probably the main take-home message I want you to have from today, is that it is kind of important to think about how you observe the simulation. I have a separate test where we do the exact same thing, but now applied to the selection function of the Gaia ESO survey. If a given time is running out, the conclusion is more or less exactly the same. How you examine the simulation is critically important. I will show you one plot which sort of demonstrate that, and that is the distribution of the stellar ages. If I took our simulation, which is the composite particles in blue, and looked at the age distribution of stars, the sort of the mean modal age, if you like, is around 8 billion years. If I selected the stars from our solar neighborhood in the same way that the Gaia ESO survey did, which is a much more sophisticated color magnitude selection from 2MASS, and then analyze what the distribution function of ages would be, then I would get something which was the red curve. So the main point you take is comparing red versus blue. And so the modal age in red, which is analyzing it correctly, if you like, is about 4 billion years. The modal age, when I just take the composite particles, 8 billion years. So there's a very significant difference in the distribution of ages if I use composite particles as opposed to sampling it correctly. This becomes critically important if you're really interested in subtle effects related to age distributions, which is the work of my PhD student, Leah Cox, who's looking at things like the age gradient in stellar halos. In the outer part of the Milky Way halo is 1 or 2 billion years younger than the inner part. And so currently we're just using a very simplistic way of analyzing the age distribution in the stellar halo using composite particles. But we need to do this a little bit more carefully. We need to actually sample the stars in the simulation the same way that the observers did, like Daniela Carolla and Tim Beers, to generate these sort of age maps. Otherwise, I've just shown you one example where there are very big differences in the ages when I use the composite approach versus the correctly sampled approach. And this is largely a big part of Leah's PhD work. So this is the last slide I just want to show you, and that is what are we doing right now? And this is Horizon Run 5. This is a simulation that's took about 3 years to run, split between Korea and Hull. It's about 350 million core hours. So for those of you who know your core hours, that's about 10 times bigger than Eagle, 10 times bigger than Illustris. Took our expertise on high resolution Zoom style simulations, which you see in the bottom right, and marrying it with the sort of gigaparsec scale simulations that our Korean collaborators are experts at. So we've moved beyond sort of the gigabyte and terabyte scale into peta and exabyte scales. The first paper was just published last week. And data mining this thing is going to be a huge amount of work. So this is just a gratuitous movie on the right of a fly-through, a part of the simulation. Everything you see there is a very well-resolved galaxy or cluster, and you can see the hot gases we go whizzing by. So it's an incredible data set. Certainly will be underpinning my STFC consolidated grant bid next week. So if you are someone who may be on the market and more successful and you want to get into data mining this thing, keep your eye on the job ads pending the outcome of the consolidated grant bid. Really exciting stuff. And that's everything. This is my summary. I'm not going to wade through the whole thing. Just take away that one sentence. How you observe your simulation can be as important as all of the gory subgrid physics that went into generating it in the first place. Thanks very much.
Wow, Brad, thank you very much. That was really, really interesting. A round of applause is always challenging on Zoom, but I can see some emojis popping up already, so that's great. I imagine there might be quite a few questions. Does anyone have one that they'd like to start off with? Let's bring up the number. Oh yeah, Simon.
Oh yeah, so very interesting stuff. So I've a question probably about some of the gory numerical details, because I'm always intrigued by this calibration of the simulations. So when you decide to calibrate on a certain observable, I know what was the main one, stellar mass to halo mass ratio.
Yeah.
And in practice, there's probably a lot of numerical knobs to turn. That's there may be several combinations that give you the same result. So how do you decide that, and how does it relate to because that's, I mean, a choice of how to turn the knobs. I mean, it amounts to a choice of physics, right? In the end, of the physical input. So how that?
Yeah, you're right, and there's no simple answer to it, in the sense that my postdoc at the time, Chris Brook, ran, I don't know, 500 versions of the same simulation, and would usually stop it at sort of redshift 2 or something like that, or 1, not take it all the way down to 0, looking at all the different knobs, which ones are, some of them are, second order in some sense, and some of them are clearly first order and do have a big effect. And so it's wading through the ones which do have a big effect, and there's going to be some degree of degeneracy. You can imagine, things like, you can mess around with your initial mass function if you want, change the relative ratios of high mass to low mass stars, change your upper mass limit in a way that you have a completely different shaped IMF but have the same fraction of high mass stars, simply by varying the upper mass limit or something, or playing around with the lower mass limit. You could mess with your IMF and then overproduce the number of high mass stars, but then turn down the feedback efficiency to try to minimize the impact of the excess of high mass stars that you've put in with your. So yes, there's going to be some degree of degeneracy hidden away inside of there, and there's no answer I'm going to give you that's going to convince you that is the right way to do it. Some things we sort of locked in, maybe in some sense, by saying, look, we think the initial mass function really is a Chabrier IMF or a Krupa IMF, and we're not going to, we can go down the road of playing around with the IMF, but we're not going to do that. We're going to take that one as sacrosanct, right or wrong. That was one of the assumptions that went in there, and that eliminates some of the degeneracies by locking in some things. But yeah, there are a whole bunch of things hidden away that both Chris and other postdoc at the time, Greg Stinson, spent all the time looking at. These were SPH simulations. The kernel shape, how many, what was the smoothing length? Did you spread things over 64 particles, 128 particles? There's a whole bunch of gory things in there that, I never got involved with whatsoever. So you do the best you can. You try to identify the ones that are second order and not first order, and you try to lock in the ones that you feel can be locked in. And the IMF was one of the ones that we decided to lock in, rightly or wrongly. But yeah, it's the devil is in the details of all those. And his parameter study was, like I said, was running about 500 different versions to redshift 1.5 or something, and trying to zero in on the parameter space where things were important versus things not being important. Never really got captured in the paper correctly, the fact that he had done all these gazillions of runs. But yeah. So that's my waffly response to that, even though you're absolutely right in asking that question.
Could I ask a question about one of the slides you showed halfway through?
Yep.
You showed the star formation rate as a function of cosmic time.
Right.
maybe you could find that slide.
Yep, the eagle, that was stolen from Eagle, I think.
Yeah, but I was particularly interested because you were saying that the big spike was associated with the thin disk.
Oh, okay, sorry. Sorry.
You could show the slide, then I could remember exactly.
Yeah, sorry. Let me just pull this one. I've got too many screens. If I can share screen, share that.
Yeah, it's the one after that.
Yeah, so it was the, I know the one you mean, it was the one showing the...
Yeah, just the one after the one you're showing at the moment.
The one after that is that one, but...
Oh, okay.
Yeah, I think it was the one that showed it was the good, the bad, and the ugly, and the good was...
It was the good, it's called the good abundance patterns or something.
Yeah. No, it wasn't that one. That one. It was going to be inside of that one.
Yeah, that's the one there on the left. Now, yep. I was puzzled because the spike on the left, that corresponds to the thin disk, if I understand correctly.
No, sorry. Yeah, some of these plots I've got time going left to right, and some of them.
Because that's confusing me because.
Yeah.
I mean, there's two spikes. There's a big spike, but there's also a second bump at about 8 gigayears.
Yeah.
So which is the thin disk?
So thin disk would be kind of everything to the right of the arrow. So if I were to put time, the better thing to do would have been to put time on this plot, the alpha to iron versus age. So the sequence across the top here would take you up to sort of 3 or 4 billion. So the first 3 billion years or so is the sequence across the top. And then roughly speaking, the last 10 billion years is the sequence along the bottom. And, that little dip that you see at 3 billion years does sort of correspond to this drop. Drop is probably too strong of a word because the scale is very small. But that is, that's what causes, or that is where this 0.05 dex drop, if you like, in the sequences occurs post this burst here.
So is the thin disk the second bump then, which is something
the thin
like
disk is basically, the thin disk is everything more or less to the right. And the problem is any sort of any other discontinuities, let's say, that might happen, say, along with, say, that little dip that occurs around 6 billion years, for example, is sort of hidden away inside of this thick blob, so you can't really see it. You can see the dip there, which is this one here, but any of the other patterns in here are hidden inside of this mess here.
So is that second bump at 6 gigayears, is that significant, or is it just a blip?
Yeah, I mean, I don't remember. So what I can't remember now is, so there's this little, 30% increase in star formation, for example, that occurs, between 7 and, it's not a perfectly smooth declining exponential. If I go from 4 to 13, yeah, there's broadly this decrease, but there's this burst of star formation at the 30% level that lasts for some period of time.
Okay, so when in your previous picture you showed the global star formation peaking at something like a redshift of 2, do I associate that with one of these peaks here? I mean,
it's a bit of a, I know what you're saying. So the cosmic star formation rate.
Yeah, the cosmic star formation.
It's sort of
a peak.
You can't really see all of which would be this one.
Yeah, the one it has a peak there at a redshift of 2. So do I identify that with the peak in your last diagram?
Yeah, you could associate that with the peak of the. I mean, it doesn't work on an individual, because this is averaged over all galaxies of all types. You have to be a little bit careful about taking one particular simulation or one particular galaxy with one particular star formation. Yes, it does happen to be that the peak that you saw about look back time 10 billion years in that simulation does coincide with this peak in the cosmic star formation rate. But galaxy by galaxy, in an average sense, that's what you would expect. But for an individual, I could pull out another simulation where the peak is earlier. I could pull out another simulation where the peak is later. It did just happen to be in that particular simulation that the peak did correspond with the globally average cosmic star formation rate.
Okay. Well, thanks for clarifying that.
Yeah, sorry.
It was a very interesting talk.
But yeah, they are going. Yes, that's a plot where look back time is going to the right. In the other plot, it was going the other. Yeah, there's no consistency in where I grabbed these plots from in terms of left to right in time.
Okay, I think we're. Oh, I see, Tom, you got your hand up. Do you want to ask the last question?
Yeah. So on the smaller scale of star formation, one of the biggest problems we're facing now, just thinking about star formation in the galaxy, is we don't actually know how molecular clouds form in the first place and how long they live for and stuff like that. But there are things like tentative correlations between molecular cloud lifetimes and things like galaxy mass. I was just wondering if these sort of larger scale simulations, are they capable of predicting how long clouds are actually molecular for, and can they maybe help us out there at all?
Yeah, I mean the ones that we've been doing, you wouldn't trust anything that. I mean, we've tried to associate. So I did some stuff with Rob Thacker, Dave Williamson, I guess, as well, where we looked at idealized simulations in a non-cosmological context, so we could crank up the resolution more. And we tried to associate some of the things that we saw with, and James Worcester as well, with giant molecular clouds, if you like. Looking at things like, in this case, maybe indirectly lifetimes. We were looking at mass functions and comparing with stuff from Claire Dobbs and Elizabeth Tasker and things like that. But the things that we were resolving, even in those idealized simulations, I think it's a great thing to do. And there are people out there who have the ability to do zoom in style simulations that could do this way better than we could do in a cosmological context. Cause again, well, the hope is over the next few years, we can start doing these things at tens of parsec resolution, the way that there's some groups, Fire 2, some of the new grids of simulations coming out are getting down to that 100 and less than 100 parsec with these zoom style cosmological runs. But I think if you want to do it properly, where you actually do resolve the molecular clouds in a way that you might trust it, rather than the things that we called molecular clouds. I'm sure if you looked at them, Tom, you go, look, these are not molecular clouds. Come on. Yeah, we were stretching the not the truth, but believability maybe by associating things with molecular clouds. I think, our cosmological runs and stuff we're doing now with Horizon Run are just not the right beast to be doing that. But the question you ask is a great one, and it's something that I wanted to be able to try to do, but I found that we had to stretch things too much with the simulations that we had. We just didn't have the in-house expertise to do it properly. So which is probably reflected in the citation rates of those papers as well.
Thank you.
Okay, so Brad, once again, thank you very much for a fantastic talk.
Good to see you guys.
And thank you for the kind of interesting discussions and stuff. Yeah, it's a shame it couldn't